Hey, what's up, guys? This is Chung here, and so today let's talk about another uh, a tree and recursion problem. Here it's called uh, all possible full binary tree, number 894. Uh, it's a classic medium problem. I think I like this problem. I'm gonna give it my own like here. So so what does this problem say, right? So let's say you're given a number, so the input is pretty straightforward, just an integer. And then you need to return all the roots node of the possible full binary tree. So what does a full binary tree mean, right? So one node can only have 0 or 2 subnodes, right? Basically, you cannot have one node only have left or right. So if a node we're having a child node, it has to be both left and the right, right? And then you need to return all the root node of this all those nodes here, all those possible full binary trees, right? And each node value will be 0. It doesn't really matter. So in this case, just 0. So um, so with this kind of every time when you guys see this kind of all possible trees, um, a key concept here is to so how should we generate, right? How should we generate the the possible subtrees, right? Because each of them will need to have like a unique root, and for each of the node here, they should be like separate, right? It cannot be you cannot simply do a DFS traverse and then you just keep distributing different nodes, because that won't work, because every time when we see a new node, we need to make a new node. Sorry, when we see a new position here, we need to use a new node. We cannot reuse the previous one, right? I think that's kind of a little bit difficult to understand here, because while we're traversing down here, right, we cannot use the previous created nodes here. So it has to be a new node every time, right? And the pattern, right? The pattern for this kind of like find all the possible trees problem. What is the pattern for that, right? So pattern is gonna be we're gonna use a recursive call, and we'll get the left. Basically, we'll get the left subtree, right? We'll get the left trees from a recursive call, a recursive call, a recursive call, right? And this recursive call, this one will return what it will return, right? It will return a, on the left side all the root nodes that can be I mean basically all the possible subtrees on the left side. Basically this recursive will return, like, let's say the root 1, right? Root 2 and the root 3. It's going to be a list of the a tree node that which represents all the possible subtrees on the left side. And then we're going to have a right, same thing, we're going to have a right trees here. Same thing for the recursive here. And here we're going to have like a root root like 4, 5, and root 6, right? Let's for just assuming on the left subtrees we have root 1, 2, 3, and on the right subtrees, the possible subtrees is root 5, 4, 5, 6. Then how are we going to return all the possible uh, trees with this tool, right? We just simply do we do a nested for loop, because we need all the combinations, right? With all those possible left and right, basically we just need to pick all the combinations between left and right, and then we construct to our current root, right? Basically, we're gonna have a left, right, left, in, left, left trees, right? And then we're gonna have a nested for loop here, right, right? I skip that. And then here, what do? Here we do a node, right? So it's gonna be a, not node. I'll just do a root here. So tree node 0, right? So basically every time, since we have all the possible left and right, so for each of the possible combinations from left and right, we need to create a new root. This is the key point here. Every time we will create a new root because each of the combination will be a new subtree, right? So we do a root dot left, right, equals to this left, and the root equals to right equals to right, right? And then all those roots here. So in the end, going to be an answer here, right? Going to be a answer here. It's going to be a list here, right? So every time we just keep adding this root inside here, and this answer will be our final result here. So basically, that's the template for all this kind of possible trees problem. So with all the possible tree problems, first step is to get the left subtrees, right? And then you do a recursive call with the with whatever you need. In this case, it's going to be the number left here, right? And then on the right, so you do the same thing for the right tree, and then you do a for loop. You do a for loop with once you have left and right, uh, select all the combinations from left and right, and then for each of the combinations, you create a new root, and then you assign the left and right to it, and then you just return this root list recursively, right? So then it will give you the final result. Cool. So that's a template. All right. So then with this template, let's see how can we solve this problem, right? So mm, okay, let's see what can we do here, right? So with number n here, right? Let's see what can we do here. We have this. Okay, so if n equals to what? If n equals to 1, right? So let's have a base point here, right? If n equals to 1, what's going to be the result, right? It's going to be return what? The uh, tree node 0, right? If there's only one node, we just need to return this tree node. Else what, right? Then if this one is bigger than 1, right? So what do? We do a for loop, right? So I think another key concept here is like, let's say we start from the root 0, from the root here, right? And at this moment, let's say yeah, let's give an example 7 here, right? So we have a 7 here, n equals to 7, right? And then we start from the first root here, right? So how can we traverse? How can we get the left and right, right? There are like different possibilities, right? See, for this one, see the left is 1, right? And the right side is like what? It's I think it's 5. Yeah, 5. And here is also 5, right? And in this case, what? The left is 3, right? So this is 1, right? Left is 1, left is 3, right? And the right side is also 3. And this, but when it comes to here, right? The left side is 5, right? So that's how we, as you can see here, so those are the numbers we can distribute to the left, right? And then we can just simply, on for the right side, we can simply use the n to subtract this left side to be the right side subtree node, right? So yeah, so basically we have, since we have that, now we can try that. We can do the coding here. Let's define the answer here, right? And because in the end, we're going to return the answer here. So what do we do here, right? Right? Let's do I here, right? In range, right? In range what? In range 1, right? Because as we notice that, right? As we notice that 0 doesn't make sense, right? 0 means it's nothing, right? So we don't have to do it, right? So, but as we notice that you can only distribute it a odd number of the nodes to each side, right? That's 1, right? Like we said, this is 1, this is 5, right? This is 3, this is 3. Why? Because if you distributed 2 to the left side, right? Let's say there's a node here and there's a left and the right. Let's say you distributed uh, if you distributed 2 to this side, right? So you have 2 on this side. There's no way you can form a full binary tree, right? I think it's pretty obvious. If you have 1 here and then what? You have 1 left, right? It has to be either this side or this side. So basically the full binary tree has to be an odd number. You cannot distribute even number on either side. So that's why we have here. So basically, when we have a number here, we have the first for loop is to try the for loop is to try all the possible distributions to the left and the right, and then we just try all the possibilities here, right? Okay, so but since we only want to try all the odd possible numbers, right? So we basically that's why we start from 1 and the step is 2 here. And then like I said, now we can have like a recursive call here. We're gonna have a sub trees here, right? Equals to the same method here. We're calling ourselves out possible full binary tree, right? And then it's gonna be I here, right? Since we're trying, so this I will be the nodes will be distributed to the left side, and then the right tree, right? The right trees will be all possible full binary tree. Then what's going to be that? So it's n plus, sorry, n minus I minus 1, right? So what is 1? 1 is the current node, right? With n here, we need to subtract 1 for this current node, right? 7, right? There's already because besides the left nodes and the right nodes, we still need a root node to construct a tree, right? That's why we need to subtract 1 here. That's the nodes we can distribute to the right side, right? So, and once we have the left trees and the right trees, which do a nested for loop here, right? We do a for left in left trees, right? And then another nested for loop right in right trees. And then every time we need to create a new node, tree node, right? So which in our case, the value is 0, and then we just do a root dot left equals to left, and root dot right equals to right, right? And then we just add. In the end, we just answer that we append, right? Append this on to the left. So what am I thinking? Root, right? And then in the end, we just return this answer. Since we're doing this recursive call, right? When this is 7, yeah, at the beginning this is 7, right? So we do we distribute it. 7, we try all the distributions we have here, and we get the left and right. And for each of the distributions, we create a root node here, and we suspend all the possible left and right, right, to the global answer here. And then in the end, we just return this answer. And this answer will also be returned here, right? Because it's a recursive call. So basically every time so this like all possible full binary tree will return all the root nodes, and we'll be using the root nodes along the way here, right? This is like actually it's kind of like top-down dynamic programming, right? Because we're using the previously calculated result. Since this is a tree, uh, as a for a tree problem, we can only use the top down because that's how we traverse down here, right? I think for this one, can we use a bottom up? Maybe. Yeah, but this like top down to think the thinking of the top down as for a tree problem is more intuitive for me. So it's easier to think it from top down because we have the root and left and right, right? And I think that should do it, right? Uh, oh, yeah. I need to redefine it at the beginning here. Cool. So see, it works. And since we mentioned it's a dynamic programming, so one of the improvements we can dynamic programming can always have is the memorization, right? As you can see here, so every time we return a answer here, but we keep for each node we keep calculating all the possible numbers here, right? We just keep doing it for each of the number here, right? So a simple right, a simple uh yeah, sorry, so with the recursion, this one uh that's the I also want to like emphasize this point one more time because with the recursion we need to have a breakpoint, right? I mean we need to have a base. Basically, n equals to 1 will be our base case because 1 we know there's only one possible trace here. If n equal to 0, that's going to be empty, right? So keep this in mind. We need to have like a base. Otherwise, if we don't have it, we're not going to return anything basically. Okay, so let's define like a global variable here, right? So let's do a self, and let's do a memorization, right? Let's do a dictionary here, right? So what's going to be the dictionary? We can do a mem1, right? Goes to what is that? Same thing here, right? Tree node. Uh, yeah, we can add 0 here, but I think we don't need add 0 because we're not going to. Do we need a 0? Let's see. 1 on the left side. No, probably not. No, since we are doing this like odd jump, every time we jump to and with this number, if this number is valid, we will always get both odd number on the left and right side. So we don't need a 0 base here. Yeah, but it doesn't hurt. I think we can add it here. It doesn't hurt. So do a 0, right? So what is 0? Basically empty, right? Empty array, right? Empty list. And here, right? So here, since we already have the memorization here, we don't need to have this base case here. Instead, we'll simply we check if n is in the memorization dictionary, right? If then we just return this, we return the self memoization dot n, right? And here, then in the end, we just need to set equals to answer, right? So that's our the memoization mm, template here. Every time we check if so we already calculated for this n, then we just simply return it. Otherwise, we in the end we just assign this answer to this memoization list. Right, so let's run this one more time. Uh, tree. Oh, sorry, typo here. Tree node. Cool. See, so now this time it's much faster, right? Almost beats 95, 95%. It's all because of this memoization here. Because we don't recalculate the number we had already calculated. So that's one of the classic improvement for any dynamic programming. And the recursive, yeah. So yeah, just to recap really quick. So with with all this kind of full binary tree problem, so we get left subtrees and right subtrees, and then we do a nested for loop to get all the combination from left and right, and then for each combination, we create a root and we assign this left to the root and the right to the root, and then in the end, we just use this root as our result. So yeah, and all this kind of case is just only for this quite specific problem because we need to decide all the possibilities on the how many nodes we need to distribute to the left and the right. All right, cool. Thank you so much for watching the video, guys, and I hope you guys like it. And yeah, I'll be seeing you guys soon. Thank you. Bye bye.